Okay, so good morning, everyone. Welcome to the last lecture of CS420 for this semester. I wanted to start off by saying thank you for sticking with us through this strange semester. Normally, you would have been in class and we would have covered about twice as much material in lecture. We wouldn't have covered more material in terms of book content, but we would have done it with twice as many lectures for each of you. So I appreciate you sticking together, sticking through this with us. It hasn't been great, but we're making the best of a situation that we have no control over. And so sometimes that's the best that we can do. Before I get started, we're going to talk about chapter 10 today from the Xi books. That's on security. And that's, of course, where we're going to end the semester. Before I get started, I did want to talk a little bit about what we can expect for the rest of the semester. Um, you should be, hopefully, if all is well, seeing the Canvas webpage for CS420 at this point in the video stream. You'll notice that lecture 14 is here. If you click on this right now, there's nothing here. I'll put up the Jamboard and the lecture video that we're recording right now after we're done talking about it. The other thing I would have you look at is the course evaluation. So there's a minuscule amount of credit available to you to try and motivate you to do the course evaluation. Oh gosh, everything's different this semester, so go easy. But the course evaluation is important to us. And then the final exam will be opening at 8 a.m. on December the 8th. So yes, what that means is for right now is that we will not be having class on the Monday or Wednesday of following Thanksgiving. Those days are open for study as far as I'm concerned. If you have questions going forward, I will certainly be available to answer them. We can hop on Zoom or you can just send me an email. This has always been the plan. This has always been the hope that we would get through with the lecture material that we expected to get through with. And that's what we're going to wrap up today. And that we would not have to kind of come back and do this virtually. But the struggle is going to be that if we take 2 weeks off effectively for Thanksgiving and then come right back and do the final exam, the what's the word I'm looking for? The temptation is going to be for you to ignore all school until you come back and you take the final exam, or you study for a day or so to get ready for the final exam. I recommend that you don't do that. You're going to need to have fresh minds when you take the final exam because it will be comprehensive, much more comprehensive than previous exams have been. Now, about that exam, obviously, I haven't made it yet, so I can't can't speak directly to what's on it. But I can tell you that it will be comprehensive and it will follow the similar formats to previous exams. Okay, so follow your study habits from last time. If you did well, improve your study habits. If you'd like to do better, but the skills that you picked up from taking the exams in previous exams in the semester are going to cross apply, and the material is obviously all going to be there as well. Okay. So course evaluations, final exam. I think that's about it for what we're about to get ready to do to close out this semester. With the exception, of course, of looking at chapter 10. Okay. So technical difficulties are happening. Let's see. Always the bane of my existence. Uh-oh. Oh boy. Okay. So let's pivot then. It doesn't look like I'll be able to make you a Jamboard today to do the notes. So let's instead let's just look directly at the notes and follow along with them. Now, that's not my favorite idea, but we'll go ahead and do it. So this is about security. The security goals are twofold. First, we want to prevent theft or damage to software or information, okay, and hardware, software, or any kind of information that that we might be having to control in our system. And we also want to prevent disruption or misdirection of system services. So no damage, no misdirection. And generally, when we talk about protection, we're talking about multiple components. The four main components that you'll see over and over when you're talking about computer security are confidentiality, keeping secure what is supposed to be secure, keeping prying eyes out of what is meant to be used by certain individuals. Okay? Integrity, making sure that the data that's there is valid. Availability, make sure that it is making sure that it is that the data and the services are available for those who should be able to use them. So like distributed denial of service attacks, for instance, or denial of service attacks in general, where maybe a website or a service is knocked offline due to illicit use, is an attack on availability. And then authenticity, excuse me, authenticity, making sure that the data that's there is authentically accurate. Okay, so table 10.1 talks about in your Xi book, it talks about several uh, types of violations, security violations, and the consequences that those security violations might have. So I'm gonna open up Zybooks over here in this other screen and take us over there. Okay, there we go. So table 10.1, information disclosure, information modification, information destruction, unauthorized use, denial of service, like I talked about, user deception. Typical consequences, violation of confidentiality or privacy of users for information disclosure, loss of information and or the ability to carry out subsequent security violations for information modification, loss of information or access to services, loss of revenue to the service provider or owner for unauthorized use, financial loss for denial of service, loss of information for user deception. Okay. All right, so one of the main types of attacks that we have to defend against are not really attacks from the outside world. Now, these numbers are these percentages are always changing, but something like 80 to 90% at one point of attacks were aided or strictly because of insider threats. Okay, these are called insider attacks in general. All right, the insider attack is an attack that is propagated or supported in some way by a legitimate user of the system, by a trusted insider. It's not easy. So don't get me wrong. It's not easy to keep the outside world out of your computer security systems, right? To build security systems that keep the outside world out. That's not easy, but it's way harder. It's way harder to keep trusted users from abusing their trust. Okay. And so this is an area that of some significant study in computer security. Right? People might be motivated by greed or revenge or just be malicious, and you've trusted them with the keys to your kingdom. So they're trusted insiders. So the kinds of attacks they might do are, logic bombs, where an unauthorized piece of code is set to execute at a specific time. They could do that because they're interested in blackmail or revenge against your company or organization. Backdoors, famously, these used to be everywhere. Um, and it would be when sort of low level, underpaid, underappreciated. I mean, even if they're highly paid and they feel like they're underappreciated. But control is offered by nerds in an organization, right? Control of the systems go through the organization's nerds. Okay. And those nerds sometimes build in, like you and me, sometimes build in backdoors. Those are mechanisms that bypass user authentication and permit unauthorized access for later use. And you can imagine how that might be problematic, especially if somebody built that in there thinking that, if anything ever happens to me, boy, will that organization be sorry, because I'll still have access. They won't know about this access, this kind of access. It's secret, so therefore they won't be able to block me from using it. Sometimes these back doors start off innocently enough. Sometimes they're put in by harried or busy professionals who are looking for a way just to, you know, secretly skip that laborious authentication process. If I could just have a simple keystroke and the system's like, it's you, and lets me in to do my job. And sometimes that seems to save a lot of time. And so sometimes it's not meant maliciously to begin with, but it becomes malicious later on. And these are things that are sort of hard to defend against, especially if you don't know they're there. Information leaking, disclosing confidential information, login spoofing. Okay, so login spoofing is different from backdoors. It's not that we're trying to get into the system or to circumvent the login system. Instead, we could, as insiders, or somebody could, as insiders, attack the system by creating a fake login screen. Okay, and so the user unknowingly is faced with a screen that says enter your username and password, and so when they do that, what that does is it is the system is the login spoofing program stores the username and password for later use somewhere secret, right? And that can happen um, potentially transparently to the user. Okay, and of course, if you have a table of username and passwords that an inside attacker can come get later, then they have all the authentication credentials they need to be whoever they want to be and do whatever they want to do on the system. This will make more sense once we spend a little bit of time talking about how passwords are generally used. Because you might be saying to yourself, well, if you're an insider and you have security clearance already, then won't you be able to see the password somewhere, right? It would make sense if you said, look, the authentication system, the security system, must have username and password pairs stored somewhere so that they can check usernames to passwords, right? Are you who you say you are? Well, how would I know? I need to store the username and the password somewhere. But it turns out that there are mechanisms in place which prevent the storage of passwords in plain text format. We'll talk about those later. Login spoofing helps us get around that. Another kind of attack is an attack that exploits human weaknesses. Okay, so these are Trojan horses, right? Where a program that appears to offer one service, but also can do damage to the system, and the user voluntarily welcomes in the program and runs it as a trusted program, and then behind the scenes, it's doing something malicious. Okay, and one of the things that it can be doing behind the scenes is installing a virus. Viruses are often transmitted using Trojan horses, and a virus is a piece of executable code that embeds itself into the legitimate programs and copies itself to other programs and systems with the intention of causing harm. Viruses are executed whenever the host program executes. They seem like they are legitimate, okay? But the side effects of the virus are anything but legitimate. They do damage, they delete, or in even the worst case, they may not just delete information, they may reveal information, or they may open up additional backdoors for other attacks to take place. Viruses, though, they rely on an infected program. Okay, that's different than a worm. which is an unauthorized program which copies itself to other networked systems via exploitation of one or more system weaknesses. Okay, one such system weakness, and this is a new category, attacks exploiting system weaknesses. One such system weakness is a potential buffer overflow attack. Now, I'm not going to go into great detail about buffer overflow attacks, but generally, how that works is some systems, in particular C and C++, allow programmers to declare buffers. Okay, and you can think of that as an array or a consecutive block of memory, and to address those using indexes. And this is something you're familiar with, right? In a C++ array. What they don't do though is they don't check to make sure that that buffer has not been exceeded, overflowed into the next location in memory. Okay. And so generally what happens is you've got bad code running somewhere or unsafe code running somewhere. And that unsafe code allows an attacker to overflow a buffer. And if that code is, say, a driver that's working in kernel space, and you'll recall that we talked about the difference between kernel space and user space when we talked about processes a couple of months ago. And this is something you're going to need to go back and remember probably. But if that is a driver running in kernel space, then one of the things you can do is potentially overwrite the buffer with a bunch of garbage until you get to a return address somewhere outside the buffer in memory. As long as you know where that return address is, you can overwrite that return address with an address of your choosing, okay? Probably back in the buffer somewhere. And so what you actually do is you fill the buffer up with a small executable program. Then you fill the rest of it up with garbage until you reach a buffer, a return address rather. And then the return address you overwrite to go back to the address where your program is, and then you run the program. Okay, that is a buffer overflow attack, all right? Because you were in kernel mode, and now you've gotten the program to accidentally run a program that you inserted into it, okay? And that program can now do anything. It can now completely pwn the system. That is a 1 or 2 minute brief overview of how that works. There's much more detail to all of this, as we'll see later. Okay, so the general problem though is if you didn't write the code yourself, okay, and I'm not just talking about programs, I'm talking about widgets, scripts, you name it, any kind of executable code, code that runs inside of applications, code that is executable code that runs on directly by the operating system, whatever, any kind of executable code. If you didn't write it yourself, then you've got to trust that whoever did write it did not embed malicious side effects, okay? You're left only to trust that it is not malicious. And how do you trust that? Okay, how do you trust that? What if you don't trust it? I don't know who wrote this code. I don't know if this code is actually a correct implementation of a solution that I need. Okay, I don't know that. So one solution is to use sandboxing. And sandboxing is where we take a small area of memory, okay, within which a program may execute and which guarantees that the program cannot access and jump to any location outside of the designated area. So this is the area where you play. If you want to execute code outside of this area, okay, you can't do that. And so this puts you in a sandbox, a safe environment where you are limited as a process to what kinds of things, what kind of memory you can manipulate. Okay? And this is one way to ensure that mobile code does not have any unintended side effects. All right, so that's just kinds of attacks and kinds of and things that we can do about it. So now section 2 in chapter 10 talks about user authentication. So user authentication is an act of verifying the identity of a person who wishes to connect to a computer or a network. And that's based on generally one of three possible kind, I don't know, strategies, let's say. One, it could be based on knowledge that the user possesses and that other people are not supposed to possess. Okay. That could be passwords. It could be security questions. It could be something that only the user is supposed to know. Okay. So that's knowledge of information. Possession of some physical artifact. Two-factor authentication, where you have a message sent to an application on your phone, or less securely through, and you should stop doing this, but less securely through text message, because SMS is actually not secure. So that's why most two-factor authentication these days, like Google Authenticator and several other applications, Duo I think does it. They all rely on application-based security. But still, you have to have, the idea is you have to have the phone associated with that particular phone number or mobile device number, the specific serial code of your phone. So you have to possess that item. Okay. More fundamentally, possession of some physical artifact could be an RSA key, or like a key fob, that when you push the button, it gives you a code, and you type that code into the system, and it lets you know, okay, this is I am the person in possession of this code, or just a scanner key or a certification key or something like that. Possession of some physical artifact. That's very hard. That makes it very hard to spoof. You have to ideally, if you're an attacker, you have to be able to either have that physical artifact, have stolen that physical artifact from a person, and that makes an attack over a great distance less likely, or you have to be able to break the security of that physical object, and make a copy of it in some fashion, which is a lot more difficult than guessing someone's password. Not impossible. Or there's the physical characteristics of or behavior of the user. This could be the geometry of your hand. Okay. I know for a while, Disney parks were giving people a device called a smart band, that they would scan, and then they would put their hand on a scanner. And the scanner didn't do anything but measure the geometry of their hand. Okay. The iris. Okay. Sort of the sci-fi idea of, look inside this iris scanner. Okay, your iris matches the iris on file, so you're in. Um, Fingerprints. Okay, fingerprints are a great old uh, venerable way to do what this basically is biometrics. Okay. It doesn't have to be your physical person, though. It could be behavior. So some systems are in places like, that know how you type your password. Okay. And so they measure the statistics about how you're typing the keys of your password to make sure that it's actually you typing this password. Some systems are like that in place. One thing you'll notice, even as we're discussing this, is uh, the most secure systems use a combination of two or all three of these types of knowledge, okay, before granting access. It's usually not just what you have or just what you know, but a combination of two of those things, or maybe not just what you know, not just your password, but also how you type your password. Okay, the characteristic, some biometric measure. Okay, and so that's what we need. That's what we end up doing. We end up combining these techniques to get the level of security that we need. So types of passwords or using passwords. Sometimes there's a one-time password. This is a password generated, given to the user, and to be used only once. Obviously, there are some limitations of this, chiefly that you're only using the password one time, and then it has to be reset to you. Okay, but in some applications, that can be fine. Okay, and one-time passwords are generally very secure. Okay, um, when you have to use the password multiple times, what you end up doing is you end up doing a one-way hash on that password. Okay. And I'm going to come back to that in just a second. I talked about that just a minute ago when we were talking about the the login spoofing. Let me come back to that in just a second. And the other one is like challenge response. And you've seen these where it's like, what's your mother's maiden name? That's a terrible example. What's your mother's maiden name? It can be looked up, right? But the way to use those really is to remember that when the system asks you, what's your mother's maiden name, you type in banana. Okay, that's kind of a challenge response that we use securely. I'm not saying your mother's maiden name is banana, but it doesn't matter what your mother's maiden name actually is. And in fact, it's better if you don't use your actual mother's maiden name. But of course, that's hard to remember. So you have to balance all those concerns. One-way hashes. So let's talk about this for just a second. What is a one-way hash? So a one-way hash is a system that takes a input and generates an output. Okay, and the way that the output is generated is such that the input that goes into the system always generates the same output. But if all you have is the output, there is no way to guess what the original input was. Okay, so whatever the input is always generates the same output. The output is called the hash value. Okay. This is a one-way hash, and it's one way because no amount of finagling with the hash value can ever reverse engineer back to the original input. Okay, and there are systems in place that do this, and I'm not going to go into great detail about those. Just in general, much of this falls under the area of security and information security, and so I hope you're encouraged to take the information security class based on this chapter, and then we'll dive into more details about that, about all this stuff. But that's what you need to know. So a one-way hash takes an input and generates an output. Okay, and it always generates the same output. So this is your password. It goes into the hash function, gets churned up, and now you have this. Okay, now the only way, given that you're using the same hash function every time, the only way for anybody to ever generate this number again, and that's the other thing that maybe I wasn't clear on, is that the hash is a one-to-one relationship. Only one value ever hashes to this hash, only one input ever hashes to this hash value. Change the input, get a different unrelated hash value. Okay, and things that are close as input are not necessarily things that are close as output. They'll be very far away. Okay, very randomized. Okay, but it's one-to-one. And the only way, if you have a hash value, the only way to generate that hash value again is to plug in the original input that originally generated this hash value, aka your password again. Okay, so what we do with passwords in systems is we don't save. Okay, we don't save a file that pairs usernames to plain text passwords. Instead, what we do is we have a file that pairs usernames to hash values of plain text passwords. Okay, and yeah. So additionally, we add a little bit of what's called randomness, a little bit of randomness to the hash value called a salt value. So we take the password, we append on a stored data somewhere. We then hash that and then store that hash value. Okay, the book does some about why we do that, but I'll suffice to say that it makes brute forcing password attacks harder to once we add some added randomness to the password. Okay, but we know what the salt is. We store the salt in the system somewhere. So every time a user has the username, the salt, and the hashed value of the password and the salt together. And the only way to get this hash value back is to plug in the password again. So we say, hey, what's your username? And you say, okay, blah, blah, blah. It's DAR4. Okay, DRAY4. Like, okay, DRAY4, I recognize that as a user. Prove it's you. And you type in your password. If you type in your password correctly, I add it to the salt, to the randomness, I hash it, and I compare the hash values. If they're the same, then it must have been that you gave me the same password that you originally set up. If they're different, then it must have been that that was not the password that we agreed upon. Okay, and so your authentication has failed. Okay, why go to that trouble? Because we don't trust insiders, right? We don't want to trust the system to be able to protect protect a single file that has everyone's password in it, plain text password. If that file ever gets lost, then our entire system breaks down. Our entire security system breaks down. Whereas if the hash values get stolen, you've got nothing. You cannot take the hash values and reverse engineer the passwords, right? That's why it's a one-way, one-to-one hash. That's what we're relying on. And that's also why, going back to my notes here, it's also why this is a kind of attack, because even insiders do not have passwords, do not have access to a file that contains passwords, because there is no such file. There's only a file that contains hashes. So login spoofing is one way to surreptitiously collect passwords. That's why that happens. Okay. All right, so we briefly talked about biometrics. All right, so let's look at table 10.2.1 in Zybooks. I thought it was a table. Huh, I wrote down the wrong thing. Let me see what I'm looking for. Oh, there it is. Yeah, so table 10.2.1. There we go. So here's a chart of kinds of biometrics. So fingerprint analysis, face recognition, hand geometry, retina scan, iris scan, signature recognition, voice analysis. Okay, and here are some like red, yellow. I'm sorry, green, yellow, red. Fingerprint analysis, very accurate, has a relatively high cost, relatively low convenience. Face recognition, not particularly accurate, not particularly costly, high convenience. Okay, and so you can kind of balance these out using this table. Low accuracy, signature recognition, low accuracy, voice analysis, low accuracy, but very convenient. So it depends on which one you choose. Depends on what kind of security system you're running here. Does it have to be super accurate? Is convenience more important? These are sometimes business decisions that we end up making. There is a fundamental problem with biometrics, though, and it comes down to type 1 and type 2 error. Type 1 errors are sometimes called false positives, and type 2 errors are sometimes called false negatives. I think there's a pretty cool, yeah. So here's the notion we're talking about. Sometimes an imposter will be attempting to get in to a system by faking biometrics. Sometimes it will be genuine attempts to get into a system. This side over here is what we call our false negatives, okay? Because it's a genuine attempt, but the system identifies it as not a genuine attempt, okay? It says, no, you're not who you say you are. It's like, yes, I am. Effectively, when you set up an iris scan, let's say, what that means is look in this camera. The camera collects the information about your iris and stores it. Okay, but there's error involved in running that again. Okay, so the next time I come around, I look in it, it stores it again, but there might be some aberration, statistical aberration about whatever number gets calculated, and it says, look, that the statistical aberration is outside of our error bound, so you fail. And that's very frustrating to a user who is the person they claim to be. Alternatively, somebody else might walk up to the iris scanner, look in, and say, look, it's me. And the statistical aberration says, oh, yeah, it does kind of look like you. It looks enough like you that I'm going to let you in. That's called a false positive. And we don't want either of these things. We don't want the system to let in people who it shouldn't let in. We don't want the system to block people who it should let in. Okay? Keep people it should out, let people in that it should. Okay? Um, type 1 error, false positives, letting people in that it shouldn't. Type 2 error, false negatives, keeping people out that it shouldn't, okay, that it should let in. The problem is that the more you try and limit false positives, the more you are going to have false negatives. And the more you try to get rid of false negatives, the more you are going to have false positives, okay? Because if you loosen your standards for what is a biometric match, okay, then you're going to decrease false negatives, but you're going to open a window for more false positives. If you tighten down your standard for what is a biometric match, then the opposite is going to happen, okay? So we're always in a tenuous position where we're sliding those tolerances, those statistical tolerances, to the place where we feel like, yes, we're as secure as we need to be, but also, we're not aggravating people. And here's the thing about aggravating people with security measures. You do not want to encourage users to circumvent security measures, right? And to a person, users will circumvent security measures if they feel like the security measures are not doing anything, right? That is to say, they walk up to the biometric scanner and 9 times out of 10, it denies them access, okay? So that's going to slow everybody down, frustrate everybody. And users are going to be motivated at that point to say, well, I'm gonna find ways around this. Okay, a user walks up, nope, no, fingerprint doesn't work, or retina scan doesn't work, or whatever. As soon as it does work, what are they gonna do? They're gonna prop the door. They're gonna, put a penny in the lock so it doesn't latch anymore. They're gonna hold the door open as a courtesy to the people in line and let everybody in, even though they're not all being certified as authentic users. And that's just for physical lock, but also, it works for software locks as well. People are motivated, and if people are motivated, then they're going to find ways around security, because they don't understand the implication, or because they don't see the implication of circumventing the security model as important as the weight of being inconvenienced by the security measures, right? And so we want to avoid that. But by avoiding that, we don't want to make our system useless in the other way, where it just lets everybody in. Okay, so it's a balancing act. It's a balancing act, and it always has been, and it always will be. I don't think there's any way theoretically around that. Okay, so let's move on to access control. So objects are software and hardware components that need to be protected. Every object in the system has OI, O sub I, which is its unique object name. OP sub I, which is an operation. Each object has a set of operations, OP sub I. Okay, those are things that can be done on that object. R sub I are the access rights that represent the ability of a process to perform an operation on an operation OP sub I on the object O sub I. So these kind of access rights are generally read, write, execute, RWX, and also O, right, which is the owner right that designates the creator of the object. So we can define with this now a protection domain. Instead of looking at every possible process, we can group them into domains, right? So a set of pairs, object and right, where rights specify what operations a process may perform on the object. So for example, file 1, you might have R and X on that object, which means to read and execute, but you don't have write on that object, okay? Instead of thinking about these for each process, we can group them into access matrices or an access matrix. This is a representation of protection domains where each row corresponds to one domain, D sub I, and each column corresponds to one object, O sub I. So the intersection represents the rights a process and D sub I has over O sub I. So if you look at 10.3.1, which I think is actually a participation activity that you're responsible for, and you are responsible for participation activities for chapter 10, you'll find that this is an example of an access matrix. You got all your domains, all your objects, and then the intersections represent a domain. A specific domain has these specific rights on these specific objects, okay? So how do we implement these things, practically speaking, inside the operating system? Two ways. One, an access list, and the other, a capability list. Okay, and this is an engineering design decision. And if you look at participation activity 10.3.5, you'll see that access lists are designed per object, and capability lists are designed per domain. Okay, so per object, you've got domain and rights. Okay, domain and rights, domain and rights. For capability list, you've got object and rights in a particular domain, object and rights in a particular domain. So it just boils down to what do you think is going to be more effective for your system? Is it going to be more effective to concern yourself by looking up columns first, or that is to say objects first? Do you have a lot of objects and fewer domains? If that's so, then you probably want to use capability lists. Do you have few domains and a lot of objects? If you have a lot of domains and a few objects, then use access lists. Okay, and again, it's a design decision, it's an engineering decision as to which one of those you use. Okay, finally, I'm just going to briefly mention section 10.4, the secure communication section. I'm going to leave it to you to read section 10.4. Section 10.4 delves into cryptography and keys and asymmetric key algorithms and the like. I didn't want to go into too much detail about that at this point because I think that we're very much, we already were with this chapter, we already were kind of stepping outside of the the immediate domain of operating systems, in my opinion. Certainly, security is a major concern with operating systems, and there are some design decisions that go into that. But security is also its own field in and of itself, and certainly the cryptography aspect of it is its own field in and of itself. It's important that you understand that material, but it's really important, I hope, that it will drive you to trying to get a deeper understanding than what the book is going to provide. Okay, so you're still responsible for section 10.4, but I'm not gonna extend this lecture any longer to go over those details because I think the book does a really good job at a high level. Okay. All right, that's it. That's chapter 10. That's the end of the lecture material that we want to go over. For your own edification, if you wanted to look at chapter 9, you'd be good to do that. But that's not part of the material that will be on the final exam. So that would just be for your own edification. Okay. All right. Well, I hope you're well. I hope you have a fantastic Thanksgiving, a great holiday, a great safe holiday. I hope you won't gather and put yourself in large groups. I know it's going to be hard. It's hard for me. I've got a big family, but we're not getting together this Thanksgiving, and I hope you won't either. I don't mean that. I don't mean that a bad way, but I hope you'll keep yourself and your family safe, and that we'll all be able to get back together in person after Christmas break. Again, going into the exam season, if you have questions, please reach out to me. It's a very uncomfortable feeling for me as a professor, very unusual to see you disappear for 2 weeks and then give you an exam. And I don't like it, but that's the best we can do, and I think it's the right call. So instead, what I'm going to do is just offer help wherever I can for you while you're studying for your final exams. Okay. Don't forget to do the reading assessment material for chapter 10. Don't forget to get your basically free points for running through the uh, course evaluation. And I will be hearing from you soon. Okay. Have a good Thanksgiving.